Today's short video is going to focus on localized bonding as it's explained by the valence bond theory. So far we've explored single bonds and how they can form using the overlap of hybridized orbitals. But what about multiple bonds, double and triple bonds? We're going to look at how bonds can be categorized as one of two types of bonds. The first type is bonds that are formed on the axis between two nuclei in the bond, and these are called sigma bonds. This is a Greek letter. It's pronounced sigma. Sigma bonds are on the axis between the two nuclei, and they're made from the overlap of hybrid orbitals in most cases, or sometimes a hybrid orbital with a 1s in a hydrogen. Here's an example of a benzene ring showing the sigma bonds that are taking place here. Each of these carbons is sp2 hybridized, which means there are 3 hybrid orbitals, and where the hybrid orbitals overlap, that's a sigma bond. We've got sigma bonds in 6 places here between carbons. And then we also have sigma bonds formed by the overlap of an sp2 hybrid orbital with a hydrogen, and that's occurring in 6 places as well. Here's the sigma bond formation in carbon dioxide. The carbon in carbon dioxide is sp2 hybridized. Let's take a closer look at what's going on with hybrid orbitals, and then let's think about what's going on with the other electrons that are present, the other orbitals that haven't hybridized. On this workspace here, I've got the same picture that we were looking at earlier. And now let's look at the hybridization that's taking place in the carbon, for example. Carbon, normally, unhybridized, unbonded carbon, is in the valence level 2s2 and 2p2. So the notation would look like this. Now imagine that it's hybridized, and it's going to hybridize, so it makes 2 sigma bonds like this. That's sp hybridization. So carbon, after hybridization here, is going to be 2 sp hybrid orbitals and then 2 unhybridized p orbitals. Because it's making 2 bonds, we've got 1 electron in each of the 2 hybrid orbitals, and then the remaining 2 electrons are in 2p unhybridized orbitals. How about the oxygens? Both oxygens look identical here. They're sp2 hybridized. Here's a normal oxygen in its valence shell. 2s is full, and 2p has got 4 electrons in it. So that's 1 full orbital and then 2 half-full orbitals. When oxygen does sp2 hybridization to form this molecule, that means I've got 3 orbitals, 2 of the p's and the s, making sp2 hybridization, and then I've got a 2p that's unhybridized. How are these electrons going to arrange themselves? Well, in carbon dioxide, the oxygen is making 1 sigma bond here. I know from drawing the Lewis structure in the past that each of these oxygens has got 2 lone pairs. Lone pairs go in hybrid orbitals, and so 4 of our electrons are going to go in sp2 hybrid orbitals. A 5th of the electrons is going to go in an sp2 hybrid orbital, and that's what makes the sigma bond. And then in our unhybridized remaining 2p orbital, the 6th electron is housed. And that's going on over here as well. So I've got another oxygen that's got a set of sp2 hybrid orbitals, lone pair, single electron, and then an unhybridized p with 1 electron in it. How are the bonds formed? Well, this sp hybrid orbital from carbon is overlapping with this sp2 hybrid orbital from one of the oxygens, and that's a sigma bond. The other sp hybrid orbital is overlapping with an sp2 hybrid orbital from the other oxygen, and that's the 2nd sigma bond to that carbon from an oxygen. Now let's think about what else is still going on here. This carbon has got 2 unhybridized p orbitals. What would that look like on this picture? One of them would be up and down like this, and that's got an electron in it. The other one would be coming out of and going back into the plane of this screen here. And that's got an electron in it as well. The oxygen has got 1 unhybridized p orbital. That would have to be 90 degrees from the plane of the sp2 hybridization. The other oxygen, same thing. Now this happens to be coming out and going into the screen. What's going on with those electrons? There's an electron here, there's an electron here, there's an electron in this orbital, and there's an electron in this orbital. Well, we know that this is a double bonded species, so there must be another type of bonding that can take place and make use of those electrons that aren't currently being used. What we'll end up seeing is overlap between this orbital and this orbital to form the second bond on the carbon-oxygen on that side. And on the left-hand side, we're going to see this orbital and this orbital overlap to make another kind of a bond. This bond is off of the axis of the sigma bond, and it's called a pi bond. So pi bonds are bonds that are off the sigma bond axis, and they're signified by the Greek letter pi, which of course everybody knows. That's how you pronounce that pi. So we've looked at the carbon-oxygen double bonds in CO2 and seen how pi bonding occurs. Let's go back and revisit that. The pi bonds form from overlap between the unhybridized p orbitals on the carbon and the oxygen. So the dashed lines here are showing pi bonds that are the second bonds in both cases between carbon and oxygen. Let's look at bonding in N2. Here are two nitrogens bonded to each other. The sigma bond is made from sp hybrid orbitals. So let's look at a nitrogen unbonded in the valence shell, full 2s, and a 2p has got 3 electrons in it, and by Hund's rule, each one has its own orbital. But with sp hybridization, nitrogen now changes to 2 sp hybrid orbitals and 2 unhybridized p's. How are they going to arrange themselves? Well, if you think about the Lewis structure for nitrogen, it's triple bonded species, and each nitrogen has got a lone pair. So that means an sp hybrid orbital has got the lone pair, and then a sigma bond is going to be created by overlap with a single electron in an sp hybrid orbital. Now, nitrogen has normally got 5 electrons, and so that leaves us with 2 more, and each one goes in a 2p hybrid orbital. The second nitrogen is going to look just like that. sp hybridization leaves 2 unhybridized p's, and this has got a lone pair and a single electron, and this has got 2 unhybridized p's with a single electron. So where does the overlap occur? Well, the sigma bond happens here. That's our sigma bond overlap. Unhybridized nitrogens are going to still have each 2 unhybridized p's. So drawing those in here, there's one of the p's straight up and down, perpendicular to the sp hybrid orbital, and then the other one is going to be into and out of the screen, also perpendicular to the sp hybrid orbitals and to the other unhybridized 2p. And this nitrogen is going to have an identical situation, one p orbital like this, second p orbital into and out of the screen. So where does our pi bond overlap take place? These 2 orbitals and these 2 orbitals are doing pi bonding. So there's a pi bond, and there's a pi bond. So the nitrogen molecule contains 1 sigma bond and 2 pi bonds, and that's what a triple bond is. Anytime you have a multiple bond, one of the bonds is always going to be a sigma bond. Any additional bonds will be pi bonds, and they'll occur off-axis. Sigma bonds are overlap of hybrid orbitals. Pi bonds are overlap of unhybridized orbitals. Well, this gives us a slightly more complete understanding of how bonding can occur because it includes multiple bond possibilities. However, we're going to look next time at an even more complete and comprehensive model of bonding. It's hard to understand. The mathematics behind it are complicated, like the mathematics behind atomic orbitals, but we can take an overview of it that gives us an explanation for things like resonance that are not explained by valence bond theory.